Now let us take a flat panel without any cracks or notches. In case of uniaxial loading, the normal stresses are equal everywhere in the panel. These stresses are defined as the uniaxial load divided by the cross-sectional area. If we now add a notch to this panel, the cross-section is locally reduced, which, according to the definition of stress, increases the stress in the cross-section under a given axial load. The stress in that cross-section, however, will not be constant. It steeply curves up towards the tip of the notch, with the highest stress right at the notch root. This concentration of stress is captured with the stress concentration factor, indicated by the parameter Kt. This factor Kt is defined as the ratio of peak stress at the notch root divided by the average nominal stress in the reduced cross-section. The higher the peak stress and the steeper the gradient, the higher the stress concentration is. If we increase the width W to infinite, we effectively created the condition that the nominal stress is equal to the applied stress. For that infinite plate, the stress concentration factor Kt can be calculated with this equation. It illustrates how Kt depends on the major and minor axis of the ellipse. Or, after rewriting, it illustrates how Kt depends on the major axis of the ellipse and the radius right at the notch root. The smaller the notch radius, the higher Kt. For a circular notch, both A and B are equal, and then from the equation it follows that the stress concentration is equal to 3. Independent of the magnitude of the stress, Kt is always 3 for a circular hole in an infinite plate. If we now zoom into the region of the notch root, we can see how the peak stress depends on the dimensions of the major and minor axis of the ellipse. What is also clearly visible is that the gradient away from the notch root are approximately the same, and that they rapidly reduce to the applied stress S. And this illustrates what is called the Saint-Venant principle. Any disturbance of the stress field by a notch is limited to the direct vicinity of that notch. Further away from the notch, the presence of that notch is hardly observed in the stress field. The definition of the stress concentration factor relates to uniaxial loading. In case multiple directions of loading are present, a superposition principle can be adopted. Stresses can be superimposed, which means that effectively the illustrated biaxial load case should be considered as two uniaxial load cases that are superimposed. For the case of biaxial tensile loading with both loads equal in magnitude, the effective peak stress imposed by loading in one direction is reduced by the load component in the other direction. Hence, the stress concentration reduces to 2. The opposite is also true. If the vertical load is tensile and the horizontal load is compressive, but equal in magnitude, the peak stress goes up to 4. This means that the stress concentration for biaxial loading may vary between 2 and 4, dependent on the combination of the load. Now, what can we learn about stress concentrations from praxis? Let us go back to the time of 1842, when a train accident occurred near Versailles. This train with 17 carriages was pulled by 3 locomotives, transporting about 1,500 passengers. The sequence of the accident was initiated by the front axle failure of the first locomotive. The second locomotive ran into the first, bursting the boiler, which subsequently ignited the fire. After investigating the accident, Rankine concluded that fatigue in combination with stress concentration has led to the front axle failure. This concentration of stress was present at transitions in the axle diameters. We can understand that when looking at this illustration. Obviously, this is not the load condition of the train front axle, but it makes the concept of stress concentration clear. Away from any transition in diameter, the stress is homogeneously distributed in the train axle. Near the transition, however, the stress redistributes from one homogeneous stress distribution to the other. It tends to follow a trajectory that concentrates stress right at the fillet radius. The smaller that radius, the more severe the stress concentration. What we also can learn from this example is that adding material to reduce the stress locally at transitions may increase the stress. The strengthening may imply weakening at particular locations. This is a lesson to be taken from this example. Stress concentrations do not only occur when we locally remove material, by cutting a hole for example, but they also occur when we add material. Reinforcements and repairs, attract stress as they impose more stiffness locally. These higher stresses, in combination with geometrical changes, lead to stress concentrations. The stress concentration factor is a linear elastic concept. Depending on the ductility of a material, peak stresses may be limited by plasticity compared to what is calculated assuming linear elasticity. This ductility is favorable in case of notches. As a result, ductile materials are less sensitive to notches compared to more brittle materials. Effectively, this means that strong and brittle materials cannot be loaded as much as weaker and more ductile materials. Or, to rephrase it differently, the strength of a ductile material can be better exploited than the strength of a brittle material.